The Arctic's glaciers are facing an irreversible decline, and the culprits are tiny yet powerful microbes. These microorganisms, often overlooked, are accelerating the melting of ice and snow, pushing the Arctic into a state of rapid transformation. Dr. Arwyn Edwards, a renowned glacier ecologist, shares his alarming experience on a Svalbard glacier. He describes a day when the heat was so intense that it felt like being in a war zone. Edwards, who has spent over 2 decades studying polar regions, is witnessing a disturbing trend. The Arctic is warming 7 times faster than the global average, and the consequences are dire. The Watchkeepers and arch-agitators of Arctic demise is how Edwards refers to the cold-adapted microbes he studies. Recent research reveals that these microbes are involved in feedback loops that speed up melting. With the majority of the planet's freshwater stored in ice and snow, and billions relying on glacier-fed rivers, the impact of these microbes is far-reaching. But here's where it gets controversial. Not all polar microbes contribute to global heating. Some populations are actually slowing down methane emissions, offering a glimmer of hope in an otherwise bleak scenario. Edwards takes us to Longyearbyen, a glacier near the world's northernmost town, to explain the overlooked life within Arctic ice and snow. He reveals that every cubic centimetre of snow on the glacier contains thousands of living cells and viruses, creating a complex microbial habitat. The organisms that can survive here are incredibly advanced evolutionarily, Edwards explains. During the summer, red pigmented algae thrive on the snow's surface, seeking sunlight for photosynthesis without getting damaged. This phenomenon, known as watermelon snow, or blood snow, was first described by Aristotle. Beneath the snow, Edwards uncovers another thriving habitat, solid glacier ice. Here, microbes flourish in extreme conditions, adapting to low temperatures, minimal nutrients, and the Arctic's unique light cycles. If I look at a glacier surface, I see a 3-dimensional bioreactor, Edwards says, highlighting the importance of these microbial communities. Embedded within the ice are cryoconite granules, which Edwards describes as the frozen rainforests of the ice. These granules are miniature ecosystems, housing diverse bacteria, fungi, viruses, and even tiny animals like tardigrades and worms. Despite their critical role, many glaciologists treat these microbial communities as impurities. Edwards argues that oceanographers would never treat fish in the sea as impurities, emphasizing the need for a shift in perspective. Microbes living on the surface of ice and snow produce dark-colored pigments to harness sunlight and protect themselves from UV radiation. They also trap dark-colored dust and debris, darkening the snow and ice, causing it to absorb more heat and melt faster, a process known as biological darkening. These microbes are responsive to global changes, such as increased nutrients from air pollution, wildfire smoke, and wind-blown dust from receding glaciers. The snowpack chemistry is now different from the pre-industrial era snow. Edwards notes, rising temperatures and longer melt seasons further fuel the growth of ice-darkening microbes. This creates a positive feedback loop. Microbes darken the ice, increasing temperatures and accelerating melt, which exposes more nutrient-rich debris, encouraging the growth of even more microbes, and so on. Each summer, a biologically darkened zone visible from space appears on the southwestern part of the Greenland ice sheet. According to a 2020 study, microbes in this region contribute to up to 13% of total melt, releasing a significant amount of water that could raise global sea levels. Beyond surface darkening, there's another threat: methane. Glaciers and permafrost in the Arctic cap vast stores of this potent greenhouse gas. But recent studies reveal that microbes thriving under glaciers can produce fresh methane. Thawing permafrost and receding glaciers can release unexpected methane emissions from deep underground. However, there's a silver lining. Specific microbial communities living in certain areas, like pingos, mounds formed by pressurized groundwater, can outcompete methane-producing microbes and actively consume methane. This is where the methanotrophs, methane eaters, are really saving the day, says Professor Andy Hodson. Standing on the Fox Fauna Glacier, Edwards describes it as terminally ill. The glacier has diminished significantly since his first visit in 2011, and he laments the lack of concern. Each glacier has its unique microbiome, sometimes hosting species found nowhere else. As Edwards searches for a particular microbial habitat he studied last year, likely lost to melt and erosion, he draws a parallel to coral reef biologists witnessing bleaching and death. These microbial species have intrinsic, scientific, and economic value. Their genetic adaptations to extreme conditions offer potential biotechnological solutions for various industries. Edwards advocates for an international repository to preserve polar microbial diversity, similar to the Global Seed Vault in Svalbard. When I retire or die, I want a microbial repository to be an enduring resource for future generations, he says, emphasizing the urgency to conserve this unique biological diversity. The impact of polar microbes extends beyond ice melt and global climate. They are the foundation of entire ecosystems, supporting visible wildlife, like the thriving beluga whales we encounter. Edwards compares his trips to the Arctic to visiting his father with vascular dementia. Each visit reveals further loss, a gradual progression that's hard to grasp day by day. The Arctic's glaciers are facing a terminal decline. And the role of microbes in this process is both fascinating and alarming. As we navigate this complex issue, what are your thoughts on the future of these fragile ecosystems and the potential solutions? Feel free to share your insights and engage in the discussion.